Hello, and thank you for attending this webinar on the new seismic inversion capabilities in the Kingdom 2015 release. My name's Adrian Brain and I work for Equipoise Software Limited, who develop Kingdom Seismic Inversion on behalf of IHS. It is an add-on package to the Kingdom software and works with either Kingdom Core or Advanced. Prior to the Kingdom 2015 release, Kingdom Seismic Inversion was known as coloured inversion. But this technique has been supplemented by the more powerful simulated annealing inversion, which is the primary focus of this webinar. The good news is that if you owned coloured inversion prior to the Kingdom 2015 release in July 2014, you get an automatic and free upgrade to the Kingdom Seismic Inversion suite. If you are unfamiliar with what seismic inversion is, I'll spend a couple of slides giving an overview of the objectives of inversion before we compare the two inversion techniques available in Kingdom Seismic Inversion. Now, the aim of seismic inversion is to transform the conventional seismic reflection signals into layered properties that distinguish different formations. When the seismic reflection signals to be inverted to conventional stack traces, typically near offset responses, the formation property of the layered model to be estimated is the acoustic impedance. Acoustic impedance is the product of the formation density and the P-wave velocity. Since we can also measure density and velocity in the well borehole through our logging tools, acoustic impedance can be extremely valuable in classifying rock and detecting the presence and effects of fluids and gas on that rock. Here's an example of a seismic section on the left-hand side, and next to it is the inverted counterpart on the right. In each section, the equivalent well data has been inserted. The synthetic seismogram on the seismic and the well acoustic impedance on the inverted section. The well acoustic impedance is of course derived by multiplying the velocity and density logs together, and it has been band limited to match the seismic frequencies in the data. The seismic section represents layers interfaces that are messed up by the presence of the seismic wavelet. The inverted section shows clearly defined rock layers without the confusing presence of the seismic wavelet and forms a far more natural image to interpret and to use for our reservoir characterization. So what are the main differences between the existing coloured inversion and the new SA or simulated annealing inversion? Looking at coloured inversion first, it generates what is best described as a pseudo-relative acoustic impedance volume. The procedure is fast and easy to run with very simple parameter setup. You can use either a single well solution or multiple well solutions, though our research and testing and the theoretical background behind the procedure indicate that there is little to be gained using a multi-well solution. The coloured inversion procedure is for post-stack seismic only, and the outputs are a seismic volume with spectral characteristics that much more closely match the well spectrum, within the bandwidth of the seismic of course. The closer tie to the well leads to more confident interpretation of rock boundaries and easier identification of impedance changes that may be caused by the presence of fluids, fracturing, etc. Coloured inversion is so quick and easy to run, there's very little reason not to use it as the main interpretation data type for all your project work. Simulated annealing, or SA for short, generates both relative acoustic impedance and an absolute acoustic impedance. The values of absolute acoustic impedance are the values of the velocity multiplied by the density. As mentioned, the absolute acoustic impedance has the wavelet removed and represents layer elastic properties rather than interface properties. The technique is highly compute intensive, though data requirements, like coloured inversion, are quite low to be able to run it. At minimum, a sonic log, time depth chart and seismic volume are all that are required. However, for an optimal result, a density log and a background velocity or impedance model are required if a full volume, rather than just a region around a selected well for example, is to be processed. Currently, the SA inversion is a single well solution. It's probably worth stating that the SA inversion doesn't actually use well directly, other than for wavelet estimation, which may be imported into the program anyway, but it's used as a starting point for the algorithm and for fine-tuning the algorithm parameters. It's not used in the trace inversion at all. The results are good for such uses as interpretation, reservoir characterisation, delineation of fluids in fluid-bearing formations where they might cause an impedance change, etc. So, what is simulated annealing as a general concept? Well, broadly speaking, it is a technique to determine which parameter values best define a known function, and is one of the many optimization techniques available. From Wikipedia, we get a mouthful of a definition. It says, simulated annealing, SA, is a generic probabilistic metaheuristic for the global optimization problem of locating a good approximation to the global optimum of a given function in a large search space. It is often used when the search space is discrete. For certain problems, simulated annealing may be more efficient than exhaustive enumeration, provided that the goal is to find an acceptably good solution in a fixed amount of time, rather than the best possible solution. Now, our objective is to generate acoustic impedance traces that, when converted to reflectivities and convolved with our seismic wavelet, result in synthetic traces that match the actual seismic. Clearly, to attempt this by exhaustive enumeration, that is, methodically trying every possible acoustic impedance trace until it matches the seismic, is way beyond the compute power we have at our disposal. Some other optimization methods can stop too quickly when coming to a solution. Simulated annealing has the distinct advantage that it can hop out of non-optimal solutions and continue to the best solution when correctly parameterized. In SA inversion, our function is a cost function containing two terms with user-definable weightings. The first term is the misfit function between the observed seismic trace and the synthetic trace, and the second term is the misfit between the trial model and a macro model. SA inversion applies the convolution model directly to achieve the required goal by forward modelling, computing the seismic responses of many impedance models in the search to determine the optimum model. An optimum model gives a predicted seismic response that matches the observed seismic trace with an acceptably low misfit error. To provide additional stability, acceptable solutions are constrained to lie between upper and lower bounds defined in terms of deviations from the macro model. This is our search space. So, SA inversion isn't an entirely push-button procedure. What are the key parameters for controlling the inversion? Well, first, most important, is the seismic wavelet, since we convolve this with each estimated reflectivity to give a synthetic trace we compare to the actual seismic trace. The seismic wavelet may be extracted from within the program itself, or you can import it from an external source. The wavelet is of key importance because we use this to compare the model trace to the seismic trace. A poor well-to-seismic tie will produce a poor inversion. Next up is the parameter space. The parameter space is the bounds within which the algorithm will attempt to model the acoustic impedance. The bounds may be derived either from the well log itself or from a separate seismic velocity or impedance volume. This will be required for lateral control away from the well location. If you're just testing a panel around the well location, then the well log itself may be a suitable function for deriving the initial bounds. Finally, the SA algorithm parameters are also very important. There are two main parameters, the initial temperature and the convergence tolerance parameters. These are simple constants, and they can be determined interactively by the user during the test phase. Obviously, the technique should be tested using model data for validation. Given a known impedance trace, here plotted in red, and with a macro model derived from a smoothed version of the input, We can create an output inversion result, which is our blacked dashed line here, that uses the macro model as a starting point and for the parameter space bounds only. In this noise-free case, we would hope for a near-perfect result which is duly achieved, in spite of the band-limited nature of the wavelet. The model and inverted impedance traces are converted to reflectivity series, and both convolved with the seismic wavelet to give the original seismic trace and the synthetic from final inversion model traces as seen on the right of the diagram. They can be subtracted from each other to give the error trace. We see a very small residual error, indicating that the inversion has produced the correct result. I cannot overemphasize that the background model is used only for the starting point and for permissible impedance bounds, and is not critical. If we used a different starting trace, and the bounds derived from well logs for example, we would eventually get to the same optimal result. The computation may be much longer. The final inversion model is encouraged to remain close to the background model by including the misfit between the inversion model and the background trend as one of the weighted cost functions. The workflow through the software is quite straightforward. Inputs are shown in blue boxes, the different processes involved are the red boxes. First of all, we select a sonic log and a time depth chart for a well. If we have a good density log, that can be selected too. Otherwise, we use Gardner's equation to generate the density from the sonic. We also select the stack volume for inversion. The log size match tool is used to find the nearest seismic trace that best matches the well, before moving into a wavelet estimation tool. If you are intending to import your own wavelet, you can select to import that wavelet here. The seismic to well synthetic scaling is then derived before we move on to fine-tuning the inversion parameters. At this point, we can choose to use an external macro model or use the well itself as the macro model for the inversion constraints. Once parameters are determined by reviewing inverted traces around the well location, we simply start the batch processing of the seismic trace data. You'll be familiar with well log data, the seismic data and wavelets, but what about this background or macro model for optimal results, and how is it used? Well, first, it provides the parameter space in which the algorithm operates. The SA inversion could be described as a model-driven inversion, but in fact is surprisingly independent of the starting model. Provided true impedance values are in the range derived from the macro model, the inversion will generate impedances that represent seismic traces. It also provides a source for the low frequencies absent from the seismic trace data to create the absolute impedance output. Traces from the macro model are incorporated into the absolute AI using a sophisticated blending technique. Here the quality of the macro model is important if the absolute AI volume is to be used for petrophysical calibration, for example. The relative acoustic impedance volumes that may be generated is independent of the macro model data. We'll now move on to the demo of the software. It's not an exhaustive look at every parameter and display in the SA program, rather a typical workflow for testing the inversion for a case study. All of the main parameters and options will be shown, and it will become clear that the inversion is highly interactive in nature. For this demo, I'm using the Golden project that may be available as part of your Kingdom installation. It's an interesting project for this demo as it has limited well log data that doesn't tie particularly strongly with the seismic data. This would lead to the expectation that inversion won't work too well. However, running a quick inversion with the available data might reveal an interesting result. Here we can see the stack section on a cross line through our well. I can zoom into the prospect at the well location, which has the sonic log posted in red and the gamma ray posted in green. We see the seismic is of apparently good quality, with the tops B46 and D11 tying to clear peaks and troughs, but at the tops tie a little uncertainly to the seismic. The true layering is confused by the presence of the seismic wavelet. If we zoom out and then zoom back in a little, we can see there is something interesting around inline 70. There is a blue, red, blue cycle in the seismic, just around 1200 milliseconds. Let's try inverting this seismic to acoustic impedance to see if we can improve our understanding of these layers in relationship both to the well and also to see if we can identify the nature of this anomaly at inline 70. Seismic Inversion is launched from the Project menu. We can use the Tools menu to select the inversion type. Here I'm changing from coloured inversion to the SA Inversion. The SA Inversion starts on the high def screen. This is a built-in tool to generate high def velocity volumes, which are highly suitable for providing the macro model used for the SA Inversion. The input volume may be a volume generated by Velpac, by dynamic depth conversion in Kingdom Advanced, or provided by an external contractor. The High Def tool is a cut-down version of the tool provided in Velpac 2015. We don't have time to cover this tool in this webcast, but it is the subject of a webcast scheduled for later this year. We will also have a webinar on the equipoisesoftware.com website that shows how High Def works if you are interested. If you're familiar with coloured inversion, the initial data selection in SA Inversion is identical. In the well tree, I select our well. The checklist bar at the top of the screen is a useful guide as it defines what is required to proceed through the software. Here I see Sonic is flashing, so I select our Sonic log for the well. Note that in the checklist bar, Sonic is now flagged as OK, but density is flashing. I seem to have a bulk density log, row B, so I'll select that. If I didn't have a density log, I could choose to generate a density log from the Sonic using Gardner's equation. So I could click on Generate with Gardner. Now in this case, it is clear that the row B log has been generated by the Gardner equation. Density can be important for modelling fluid effects, so use one if you have one. I then choose the time depth chart. If you have multiple TD charts, the currently active one is highlighted. I'm taken straight into the log calibration screen. The difference between the TD chart points and the integrated Sonic log is displayed as a drift curve in the middle window, and this is applied to the original Sonic log to give a calibrated Sonic log. We can see some points are highlighted in red on the curve, and we can see in the console window down here they've got quite low interval velocities. But as these are largely in the shallow section, I'm not particularly worried about fixing those. Various editing functions for the TD chart and fitting functions for the drift curve are available, but this data looks fine, so I'll leave it well alone. The green calibrated Sonic versus the black uncalibrated log are shown in the right-hand panel. I can bring the calibrated and uncalibrated log to the front of the display. I can save this calibrated log back to the Kingdom database to avoid having to calibrate it again in the future. I shall call this Cal1 and save it to the project database. From this point onwards, the well is time to depth converted using the calibrated Sonic log, not the selected time depth chart. The checklist is flashing survey, so I can select our survey data in the surveys tree. I'm going to use my amplitudes volume. We are taken to the log size match screen. This is dominated by a grid display of the predictability values of the seismic traces to the well, indicated by a large black dot. If the well was deviated, the trajectory would be plotted as a black line. Now, I'm working on quite a low resolution screen for this webcast, so what I'm going to do is detach the console window from the display and just drag it out of the way, just to give us more screen space to work with. The default area around the well is an 8x8 trace matrix, inline across the x-axis, cross-line up the y-axis. This can easily be adjusted using the number of trace controls down here. Of course, if you were using a 2D seismic line, the display would show a single column of traces, either side of the well. The impedance log and the nearest trace is shown on the left-hand panel. We know our zone of interest is towards and in fact above the top of the log, so I'll select a time window of say 1300 to 1600 milliseconds. The best match location, highlighted by the red dot, is a few traces away, with quite a low predictability of 0.37. Which could be better, but it is just about workable. The time shift display indicates there isn't much vertical shifting required to tie the well to the seismic, just a few samples in most cases. For our selected best trace match location, we have a shift of -4 milliseconds, which is a single sample. The yellow dot is the currently selected best trace location. I can choose to use the actual well location using the trace used for inversion drop-down. This puts the yellow dot back at our original well location to the nearest trace. However, I'm going to use our best correlation position as I need to extract a wavelet as best we can. Log size match is important as it can tell you quickly whether there is any correlation of the well to the seismic. The best tie location determines the estimated wavelet, the scaling of the seismic to the synthetic required, and also the optimal inversion parameters. So it is important to evaluate the well to seismic correlation for your selected well in seismic volume. Garbage in, garbage out, as they say. The red Next button is flashing, which is the software indicating it has all the parameters ready to move on to the next screen. Note that I can return to the log size match screen at any point in the workflow, should I wish to adjust the best match location. I'll press the Next button, and this takes us to the wavelet estimation screen. The only method for wavelet estimation currently supported is the Roy-White method, with parameters once again specified at the bottom of the display here. I'm going to use a window of 1280 to 1580 milliseconds. It's maybe a little on the short side, but I want to avoid edge effects with the wavelet. The estimated wavelet is shown along with panels of the log reflectivity coefficients in green, the seismic in blue, synthetic traces in brown, and the error trace, which is the seismic minus the synthetic, in pink over here. I'll zoom over our window of interest. Over our target window, we can see we have a good correlation between the seismic and synthetic traces. We have a correlation coefficient of 0.59 for the synthetic to seismic match, which isn't bad if you value these metrics, so I'll stick with this wavelet. Ordinarily, I'd recommend spending time to get the best wavelet you can for the time window under analysis. We can use the Wavelets and Spectra tab to see the wavelet in detail. In the upper two plots, the wavelet is shown in the normal and wrapped forms, that's green and orange. The amplitude and phase spectra are shown below. Note our wavelet peaks at around 40 Hz, so we have to be careful not to invert much above that, otherwise we'll be introducing noise. ASCII format wavelets can be imported on the Import Wavelet tab. The file should consist of 2 columns of time and amplitude pairs. For example, I have a Ricoh 50 Hz 4 millisecond wavelet here, and I could choose to use that for SA Inversion. Be sure to toggle on the option, otherwise the estimated wavelet will be used, not the imported wavelet. We can move to the Wavelets and Spectra tab to see the imported wavelet characteristics, just as with our estimated wavelet. However, I wish to use the estimated wavelet, so I can return to the Import Wavelet tab, ignore the message prompt, and toggle off Use this for SA Inversion. Note that wavelets and other data can be exported from the SA Inversion program as ASCII data using the Export menu option up here. The flashing red Next button indicates the application is happy that we have all the data required to proceed, so we can press the button to move to the next screen. This is the seismic to synthetic scaling screen, where the ratio of amplitude values, seismic to synthetic, is computed. This can be adjusted later, so I'll just use the default parameters for now. Now, the next button isn't flashing, so I can't proceed as some data is required. In the checklist bar, I can see detailed velocity is flashing as select. The software needs a detailed velocity volume or macro model before it can do anything else. I have 2 options in the macro model drop-down: select a velocity volume or use the well log as the macro model. As discussed before, the model is not as critical to the SA inversion as most of the model-driven inversions available. If you are evaluating the technique in a small panel of traces around the well, go ahead and select from log. However, this might not be appropriate for most projects because if you have structure or spatial variation in low frequencies, a single log obviously cannot capture lateral variations, so you would need to specify a background model. In this case, as we have seen, I've got layer cake geology, so I can reasonably use the well log itself as the background model. With that data requirement satisfied, I'm taken to the SA Inversion display where I can fine-tune the algorithm parameters. The busy main panel displays the well impedance log in red, and the inverted impedance log in black, along with the macro model in blue. The bounds and adjusted bounds are derived from the macro model using the delta max p parameter on the Inversion Calculation Parameters tab. Individual traces can be turned off and on to clean up the display. I'm also going to zoom over our window of interest from about 1300 to 1600 milliseconds. I'll apply some vertical smoothing to the macro model, just to show that it has relatively little effect on the inversion. I set smooth to be true, and I'm going to set the smooth width to be 10. Press the Apply Changes button. Before I press Apply, I'll just bring back the console window, just so you can see what's happening. When I hit Apply, I can see that we have 10 traces being modelled in the console window. These are shown in this panel here on the main display. What the central plot shows is the construction of a synthetic impedance log that as closely resembles the actual well impedance log as possible, using the macro model as a starting estimate and operating within the macro model bounds, utilising the SA Inversion parameters set in the parameters list over here. In essence, we are using the well acoustic impedance as model data to fine-tune the parameters. It's very important to remember that the well data actually isn't used in the inversion at all, so there is no self-fulfilling closed loop to worry about. Our actual objective is to reconstruct the seismic, which has a different frequency content than the time-sampled well log. The panels on the right show the 10 input seismic traces adjacent to the well, the synthetic section, and the error trace display. The middle panel, the synthetic section, is derived from the SA modelled impedance, converted to reflectivity and convolved with our wavelet, then scaled by our seismic scaler. The error trace is the difference between the inverted synthetics and the corresponding input seismic. The smaller the difference, the better the inversion. These last two panels are important to monitor as we test different parameters. We can see we have a reasonable match between the seismic and synthetic traces derived from the SA impedances already. The most important inversion algorithm parameters to tune are the EPS and T0 parameters. Guidance is given as to their ranges in the tooltip area below the parameter bank. T0 is the initial energy given to the SA model, and EPS is the convergence tolerance. The key is to balance keeping a good result and getting a sensible runtime. For example, if I change the convergence tolerance parameter, EPS, from 0.01 to 0.001, the inversion runs visibly more slowly. However, the result on the model data looks somewhat better. I can test if injecting some more energy into the annealing helps, so I'll bump up the initial parameter T0. I should go from 0.05 to, let's say, 0.08. There's a small improvement, and runtime isn't noticeably increased, so I'll keep that value. Remember on the seismic to synthetic scaling screen, I didn't spend any time adjusting the windowing parameters. I can adjust that seismic scaling parameter here by changing it to, for example, 0.01 and pressing apply. There's a slightly better visual match between the inverted impedance and the impedance log. We can interact with the other parameters in the same way to see what happens before generating the volume. We also have a different view of the data on the seismic section view screen. I can use this widget to zoom in, and what we see are the seismic traces around the well. Here we're looking at the relative impedance. What I can do is adjust the number of traces from 10 to 50 on the Seismic Data and Display tab. I can adjust the display gains and colour bars here. So I'll set the colour bar to the colour bar we used in the Kingdom project. In addition to the relative acoustic impedance display, we can look at the data in the absolute impedance domain. Obviously I need to turn off the fill wiggle option. So we can compare the well ABS AI with the seismic ABS AI. Had we used a macro model, we could also review the macro model data. We've spent time adjusting the inversion parameters and are now in a position to generate the velocity volume. Just like coloured inversion, the Apply to Volume tab becomes available when you have everything ready. We select our input volume in the left-hand tree. Here we're just processing the 3D migration survey amplitudes volume, and we can create volumes for absolute and relative acoustic impedance. I will call it demo abs AI, and for the relative volume, toggle on relative and call it demo rel AI. We can do targeted processing, so we can process between constant times or between grids with an offset above and below the first grid respectively. I just need to process from the start time down to about 2 seconds. We can specify the trace range to process. By default, the whole volume is selected. And we can also choose where the macro model comes from for the final processing. Here I'm going to use the log again. We can also specify how many CPU cores to use. Here I have 12 available, so I'll run the job using 10 cores so as not to lock up my computer. When ready, I just hit the invert selected button to start the job running. An initialization phase takes place, which can take a few minutes, so I'll pause the video until the batch mode actually starts. When the batch processing actually starts, I get a progress chart for each core. Note you can still use the main Kingdom application whilst the inversion runs. In Kingdom. Now, a small survey like this may take an hour or so to process. Larger surveys tend to be overnight jobs. I'll pause the video until the job is finished running. The inversion job is now completed running, with relative and absolute acoustic impedance volumes written back to the Kingdom project. I can now exit inversion, but there is a quirk where I have to close and reopen the Kingdom project to see the new volumes. We can now compare the inversion results with the original seismic. I've set the colour bar for the impedance volumes to the same as the seismic for fair comparison, although often selecting a colour palette with colours that emphasise low and high impedance values helps to isolate areas bearing fluids, exhibiting fracturing, etc. Looking at the stack section, RB46 formation is a peak, and D11, for example, is a trough. And other tops are fairly indeterminate on the seismic. If I change the type to show the relative acoustic impedance, this is our demo rel AI volume, the B46 and D11 tops are now at the interface between events, and other tops tie more naturally with the relative impedance section. This section also looks to have slightly improved resolution over the input seismic. The SA Inversion makes the relative acoustic impedance traces from an estimated impedance, so the seismic wavelet isn't incorporated into this data type at all, and there are obviously no phase issues to worry about. This result is evidently a marked improvement over typical seismic cleanup procedures such as decon, wavelet processing, FK filtering, and even coloured inversion, for example. We can flip the display to absolute acoustic impedance. Our demo abs AI section. The feature at inline 70 now stands out very clearly as a low impedance isolated geobody. In fact, it is a sand channel. With absolute acoustic impedance, we are looking at a layer property section, and the geobody has now a clearly defined upper and lower boundary, so we will be able to make a much more accurate delineation of this body than using just the seismic section alone. What's more, looking at the abs AI section for, say, inline 70, We can identify smaller channels as part of this complex, which just aren't visible on the seismic section. We can also look at time slices through this channel. The absolute acoustic impedance slice shows better definition of the sound channel, and the discontinuities in the sound channel are much clearer here and here, which may be significant in determining reservoir connectivity and reserves estimation. Moving up to 1204 milliseconds, for example, we can also see the outline of ancillary channels on the impedance map, just through here, simply indistinguishable on the stack slice. This could be a prospect worth investigating. It's probably worth noting that if we used a background velocity model and spent more time estimating a good wavelet, we could probably improve the result quite significantly. Given we have an estimate of the rock acoustic impedance, we can take things a lot further from our qualitative interpretation into the realms of petrophysical quantification. If we can determine a correlation between acoustic impedance and, say, porosity or water saturation in our sounds in the well logs, it is a simple matter of applying that transform to our absolute acoustic impedance volume to generate a porosity or water saturation volume. The workflow is out of scope at this presentation, but you can use the tools in Geosyn to cross-plot log and seismic attribute data to determine petrophysical relationships, and then use the trace calculator to apply these relationships to generate petrophysical volumes. Thank you for attending this presentation. I hope you found it informative and maybe even a little entertaining. The next webcast in this series will occur on the 13th of August and is entitled Injecting Some Geology into the 3D World, and we'll look at the new enhancements to ViewPack in Kingdom 2015. Thank you once again.